right, I've got an example up on the board. S, our surface, is going to be the portion of this cone, z equals root x squared plus y squared, below the plane z equals 2. So, I know what that looks like. That's just this lovely cone that opens up, and it's just the surface of that cone. Okay. Now, I'm going to say that rho of x, y, z is x squared plus y squared plus z squared. That's going to be the density function. So that's giving me mass per unit area. Okay. And I didn't bother to name the units, but maybe it's grams per square inch or something. And what I want to do is find the mass of S. Okay. So I know that that's going to just involve integrating the density function. So we're integrating over S, rho of x, y, z, ds. Again, these s's aren't the same. This is with respect to surface area. This is just the name of the surface. So we're doing the double integral over S of x squared plus y squared plus z squared ds. Okay. And I'm going to need to parameterize this so that I can switch to working in the parameter plane. Just a reminder here, this does give me z as a function of x and y, and I do, when I have something like that, have a parameterization where I can set x equal to u, y equal to v, and then z just becomes a function of u and v. However, I want to be very, very careful when there are square roots in my function. I know that the square root of at the origin would be 0, and the origin is definitely going to be included in the region over which I'm integrating here. And if I take my partial derivatives, that square root ends up in the denominator. So I would have a 0 in the denominator. It would be an improper integral. So I am not going to use that parameterization. What I'm going to do instead is say in cylindrical coordinates, that would just be r. Let's parameterize using cylindrical coordinates instead. Okay. So I'm going to say that r of r theta is x's is always just r cosine theta, y is r sine theta, and now z is r. Okay. Now, the region over which this is defined would be this disk of radius 2, because this is the plane z equals 2, and of course that's going to intersect the cone z equals r when r is equal to 2. But I do want to be careful because I'm not mapping from the xy plane to my surface. I'm mapping from the r theta plane. So I know that that disk is defined by the constant r and theta boundaries. R goes from 0 to 2, and theta goes from 0 to 2 pi. This rectangle in the r theta plane is the region over which I'm integrating. And I will not be switching to polar coordinates at any point. The r and theta take on their role as polar coordinates or as cylindrical coordinates in 3 space by virtue of this parameterization. Okay, excellent. So that's going to allow me to express my integrand in terms of r's and thetas. I'm going to also need to calculate the scaling factor I get when I switch from a ds to a dA in the r theta plane. So for that I need my two partials. So the partial of r with respect to r is just cosine theta, sine theta 1. The partial of r with respect to theta is going to be negative r sine theta, r cosine theta 0. All right, so I'm going to need to calculate the cross product of those two partials. Oops, let's keep that parameterization up. And then the magnitude of that cross product. So del r crossed with del r del theta is going to be the symbolic determinant I, j, k, cosine theta, sine theta 1, negative r sine theta, r cosine theta 0. So the I component, I'm going to get nothing minus r cosine theta. For the j component, remember to do it backwards, I'm going to get negative r sine theta minus nothing. And for the k component, I'm going to get r cosine squared minus a negative r sine squared. So that's r cosine squared theta plus r sine squared theta. And of course I can factor out that r, and that's just going to be r times cosine squared theta plus sine squared theta, and that is just 1. So my third component here is actually just r. So I'm getting negative r cosine theta, negative r sine theta, r. Okay, so if I calculate the magnitude of this, del r, crossed with del r, del theta, that's going to be the square root of this squared will be r squared cosine squared theta, plus this squared will be r squared sine squared theta, plus this squared will be r squared. So I can factor out an r squared, actually from all three terms. That's going to give me r squared times cosine squared theta plus sine squared theta plus 1. This, of course, is just 1. So I'm getting the square root of 2r squared. So that's going to be the absolute value of r times the square root of 2. If we remember, our domain D in the r theta plane, r was going from 0 to 2, and theta was going from 0 to 2 pi. So my r is bigger than or equal to 0, and so I'm just getting r root 2. Excellent. Okay, so that is going to be my scaling factor. So now, let's write out our integral. So we were doing the double integral over s of x squared plus y squared plus z squared with respect to surface area. Remember, our parameterization was r of r theta equals r cosine theta, r sine theta, r. Okay, so I know this is going to become the double integral over d. Okay. Now I'm going to just rewrite that integrand in terms of r and theta. Now, because I've chosen my parameters so that once I apply this transformation, they take on their role as cylindrical coordinates, I can just go right to x squared plus y squared. That was r squared. That's going to be r squared cosine squared plus r squared sine squared. Totally fine to go right to. That's just r squared. Plus z squared is plus another r squared. And then I'm going to get my scaling factor that allows me to switch from ds to dA. And that scaling factor for a surface integral is the magnitude of the cross product of those two partials. And that's what we had just calculated. That was r times the square root of 2. All right, this is looking pretty good. I think I'm going to rewrite this as an iterated integral and go ahead and factor out that constant of root 2. So I'm going to have root 2. We're integrating from 0 to 2 pi. We're integrating from 0 to 2. That's going to be r squared plus r squared is 2r squared times r is 2r cubed. And we're integrating then dr d theta. I'm going to go ahead and factor out that 2 as well. So this becomes 2 root 2 integral 0 to 2 pi. I'm going to get r to the 4th over 4 evaluated between 2 and 0. And then I'll still have to do the integration with respect to theta. 2 to the 4th is 16. 16 fourths is 4. So I'm getting 2 root 2 integral 0 to 2 pi of 4 d theta. And that's just a constant. So I'm going to get this constant times that constant times the length of this interval, which is 2 pi. So let's see, that's 16 root 2 times pi. And this is one of those situations where we were finding a mass, which I know cannot be negative, so I'm very happy to see that we did in fact get a positive answer.